Yeah, I see this recording now. Okay. Yeah, thank you for telling me that. Okay. Okay. So for the first question, we have random samples. They are from the uniform distribution, little etc. And then we have S1 to Sn, they are order statistic. And we have to want to show that they are these and these are independent. So I'll give you a hint. Here you have to use this formula to find the distribution of S1 and Sn, joint distribution. And you have to check, you can separate S1 and Sn. Then you can say it's independent. So like the, yes. So if the joint distribution of this one can be equal to this, if only if is S1 divided by Sn. S1, Sn, they are independent. Okay. So this is the first question. And the rest of the question is about check the sufficiency. In the second one is you have sufficient statistic. How about you do question 1 first, and then we do the rest of sufficient question, sufficient statistic question. Okay. So I'll give you around 5 minutes to solve for question 1. Yeah. So the first day is fine. You have to check they are independent. Oh, you also have to find the distribution of the S1 divided by Sn. And then you have to check independent. If you have any question, feel free to let me know. Now we are doing question 1. So for the people who just come in, and you can download the discussion handout in the Canvas. Okay. So, do you need more time? Or can I go through the question one? Okay, for question one. Okay. Question one. We have the S1, S2 to Sn. They are uniform distribution with Lino and sigma. And this is the order statistic. And we want to check the S1 divided by Sn. They are independent. Okay, the first step, we want to find the joint distribution of S1 and Sn. So what should we do is like this. S1, Sn for A and B. This is should be the equal to n factorial divided by n minus 2 factorial. And the density of A and the density of B and the CDF of B minus CDF of A to a power n minus 2. Okay. And there's an indicator function, like the B should be larger than A. Okay. And now we plug in the density. So it should be, this is n minus 1. The density of FA is the 1 over theta. Indicator function A should be greater than 0, smaller than 1. The B is the same. Indicator function 1. And the CDF of this is equal to B minus A divided by theta to the power n minus 2. Okay, and the indicator function B greater than A. Okay. And we can do some rearrangement. You can become like this. B minus n to a negative power n. And B minus A to a power n minus 2. And we can combine these three indicator function. Then we can have something like this. Okay. It's very important to keep the indicator function. So that is the density of F1, Fn. And then we want to do some change of variable. So we can define y equal to S1 divided by Sn. And the z equal to Sn. Okay. So we want to do a change of variable. The first step you have to do is find a Jacobian matrix. Okay. So the Jacobian vector is thing like this: partial y partial z divided by partial x 1 partial xn. Okay. So from the definition, this is the first one is the y divided partial derivative with respect to s1, so it should be Sn. And the second component is S1 negative. And this part is 0 and this is 1. So this is Jacobi vector, but we want to find the determinant. So the determinant of this matrix is equal to 1 divided by Sn. Okay. Okay. Then we can use the formula of a change of variable, which is the function f is y and z equal to f s1 sn multiplies the multiply the Jacobian vector. In this case, it should be 1. Okay. And this one is the inverse of this is the inverse of this one. So this whole term is equal to Sn. So we should be, this is A and B. This should be n minus 1, n minus 1, and sigma to the negative power n, b minus a to n minus 2, and we have our extra Sn, so which is Sn is b, and the indicator function, yes. But here we want to change the a and b to y and z. So, okay. A is equal to y is equal to a divided by b, and z is equal to b. So a minus b is equal b minus a is equal to so b dx, so d 1 minus y, so b, okay. So then this can become this like this. Z 1 minus y to the power n minus 2. B is z. And here you have to be careful about the indicator function. So the domain of a z is from 0 to 1. And because the S1 is smaller than Sn, so we have additional indicator function is y also is 0 and 1. This is because the S1, Sn now from 0 to 1. Okay. So now we can separate the y and z like this. So z n minus 1 indicator function z greater than 0, smaller than 1. And another one is z y to the power n minus 2 indicator function. Okay. So we have two terms, this term and this term. So we can say it should be some function of the z multiplies the, so that can imply the z is related to y. Then we complete the proof. Okay. Any questions so far? How to change your variable is very important. So you have to remember how to use the formula. Okay. Any questions so far? Why is an indicator function? Ah, sorry, it should be theta. Okay, my fault. Sorry, so this is theta. Yeah, thank you very much. Theta. Okay. Theta, theta. Here is also theta. Yeah, thank you. It's theta. But here's one. Okay. I don't see Sn10. Why we miss Jacobian in the first line? Do we miss a Jacobian in the first line? Okay. We miss a Jacobian in the first line. This line. Oh, this line. Oh, it's here. So I use the, it's this one. See, okay. Yeah, okay. Yeah, because yeah, I changed the Sn to B. Yeah. Yeah, thank you. Any questions? Yeah. And sometimes you may forget how to use the formula. A way to remember is like this. So the density of a y, so if y is equal to some function of x, then the density of a y is equal to the CDF of y smaller than y. And this is equal to smaller than y. Okay. And this can be the density of fx. Okay. Okay, so this is a Okay. So if no have a question, let's go to 2, 3, and 4. These 3 questions are related to the sufficient statistic. The first one is, so if a t is sufficient statistic and t is a function of s, and we want to prove s is sufficient. Okay. So this one you can use the definition, or you can also use the factorized theory. Yeah. And 3 and 4 are okay. The question 3 is we have S1 to Sn. They are exponential distribution. So here's the density. And we want to find a sufficient statistic. Okay. The best way to do this is also use the factorized theory. The last one is also the same. We have to use the factorized theory. Okay. Okay. Okay, so now try question 2, 3, and 4. So I'll give you around 10 minutes until 11:15.
Could you go back to the answer to 1?
Answer 1, okay. Yeah.
I just wanted to be able to copy it down.
I will submit this document after the discussion. Okay. Okay, so now is
Could I ask again a quick question about the answer to problem 1?
sure.
How did you get the separate densities of z and y?
Oh, okay. So because we can separate this into 2 terms. Okay. So this is only have y, and this only have z. Here's only y. Okay. So okay, and the density of Fd is equal to how about I writing on this? So this is equal to some function g of z multiply some function h of y. Then the density of z is equal to integrated function, integrate of fyz, yz, dy. So this is equal to integral of g of z, hy, dy. And this is equal to g of z multiply some like this. And this is a constant. Okay. And you can do the same thing, like the fy dv, and it can be equal to some h multiply some constant. Okay. And you combine these two, then you can see you can see that it will be kind of this and this. Okay. Does it make sense? Yeah.
Yeah, so basically, as soon as we see that the joint distribution is sort of separable into the two different variables, we can see that they're independent.
Yes.
Okay.
So you can only say is simple. Define independent. Okay.
Okay, thank you.
Yeah, you're welcome. Okay, let's go through the question. Okay, the question 2. If T is sufficient. Okay, I just realized it's very hard to check the definition. Yeah, so please use the factorial theory. Okay. Q is sufficient, and we have the T is equal to phi of S. Then it can imply phi S is sufficient. Okay. By the factorization theory, we know that the density of X condition at theta can be written as the function g of theta of function t and another function h of x. Okay. And this is okay, t of x. And this one is equal to g of theta, and t is equal to phi of s. So it's a phi circle s of x. So, and this is equal to, we can write it in this form. So this is another function and it's only defined as S. So by the factorized theory, S is sufficient.
So here the condition of dependency on theta won't matter. Like we can take the convolution of a function phi which is not conditioned on theta, whereas g is conditioned given a theta.
Yes, give us theta. So sorry. Let me check. Oh, okay. Okay, write in this form. Okay. So how about I write in this form? So it's a g of t of x condition on theta. So it can become like the what's this? So it can like a g. So this look like as a function of s. Okay. So this is equal to some g prime s of x condition of theta. Then we can use the factorized theory again to check this is sufficient. So you just say that, yes, that's true. Yeah, Amber, you're right. So if we can separate the s and theta, so this is a function of s and theta, and this is only a function only depend on x. Then we can apply a factorized theory to say that s is sufficient. Okay. So the key is to separate s and theta. Separate these two terms. Yeah, these two terms. Okay, does it make sense? Okay. Any more questions? Okay, and let's go to question 3. Okay. Question 3. In question 3, we have what? Exponential distribution and theta. So okay. So we have S1, S2, to Sn. Now follow the exponential and theta. So that means the densities look like this. Theta over 1 exponential negative x minus a divided by theta, and the indicator function x greater than a. And we want to find a sufficient solidity. So fine. Okay, So now we have the f. I usually use this notation. Okay, so this is equal to this is equal to the product of density. So and this is equal to this 1 over theta exponential negative si minus a divided by theta. And the indicator function si greater than a. And then we can have the this summation si minus n a s a and the product of indicator function. This term is equal to indicator function of the smallest one, s1, is greater than a. Okay. So from this, we can see it can be okay. So you can see this is a function g oh, s1 okay. And the h, this is 1. Then we can apply the factorial theory. So okay. Okay. Any
Here,
huh?
what is h of x?
You mean this term?
Yes, yes.
This term can be 1 because you can let this term to be g.
Oh, okay.
Yeah. Okay. Any more? How do you know that the summation si? Okay, that's great. Yeah. T cannot depend on the parameter. Cannot depend on the parameter. Yes, the sufficient statistic cannot depend on the parameter. It should be a statistic cannot depend on parameter. Okay. And we want to find a sufficient statistic, so it cannot depend on the parameter. Yeah. Yeah, very good. Okay. And next question is okay. Question 4. We have the y, which is a binomial distribution with n and pi. And x condition on y, is a binomial distribution of y and p. Okay. And only p is unknown. And we have to check s or y, whether x or y is sufficient. So the same way, we had to write down the density first. So f yx, this can be equal to fyy multiplied s condition on y. X. Okay. So it can be like the binomial density. So it's n choose y pi to a power y and 1 minus pi to a power n minus y. And this one is have a density this. So it should be y choose the x and p to a power x 1 minus p to a power 1 minus x. Okay. So only p is unknown. So this term can be seen as a function of h x and y. So it should be, so we only have to check whether this one can be separate. Okay. So this is how about p1 minus p to power x? Okay. And we cannot separate this term. Then like for this term, we cannot separate s and p. And also this term, we cannot separate the x and y and p. So that means x is not sufficient. Y is also not sufficient. And but if we combine s and y, is sufficient. Okay. Okay, any questions? So basically, for the sufficient question, you have to use a factorized theory. Factorization theory, yeah. This one is a if and only if. So it would be very useful for healthy to find a sufficient statistic. Yeah. And for the order statistic, you have to use this formula. You don't have to remember it, but yeah, you have to use this. And sometimes you will ask you to do the change of variable. Yeah. So yes, so that's all. Any questions?
So if we are given a sample of numbers and we don't know the distribution of it, can we still evaluate any sufficient statistics for that sample?
So do you mean if we don't know the distribution?
If we are not aware of the distribution, but we are just given some numbers, can we still have sufficient statistics for that sample?
Uh, if we don't know the distribution, I think it's really hard to do that. Yeah. So the factorized series basis is the solution is highly depend on the distribution. So like the definition, it's a conditional distribution. So if you don't have a distribution, that would be very hard. Yeah. Okay. Yeah, did I answer your question?
Yes.
Yeah. Yeah. Thank you. Yeah. Any more questions? So if you don't have questions, I think next to this discussion, you're free to go now. And I will submit a handout and video after the class. Yeah. And if you need any help, feel free to let me know.